Okay, this will be the second lecture, which is on section 6.2 and discusses orthogonal sets. So I start with a definition of the concept and then I will explain its significance. Definition, a set of vectors, v1 and a dot vm in Rn. So each vector has length n, and there are m of them, is orthogonal if each vector vi is orthogonal to every other vector in the set not equal to vi. So the set is orthogonal if it has this property. Let me just give you an example for three vectors instead of this is the general definition, but here's what it means. Suppose we have a set of three vectors v1, v2, v3. The size of the vectors can be arbitrary. For example, it could be in R5. Right, and then is orthogonal if v1, v2 is 0, v1, v3 is 0, and v2, v3 is 0, where the dot denotes the inner product. Okay, so or the dot product, which was discussed in the last lecture. So the set is orthogonal if this is true. Of course, you don't include v1 dot v1 because that will not be 0 unless v1 itself is the 0 vector. So the indices really have to be distinct. So v1 is orthogonal to v2, v3, v2 is orthogonal to v1 and v3, and v3 is orthogonal to v2 and v1. All right. Now, example. Suppose we have three vectors. 5, minus 4, 0, 3. Minus 4, 1, minus 3. 8 and 3, 3, 5, minus 1. And the question is determine if this set is orthogonal or not. So what you need to do is to compute the inner product of the first vector with other two, and then compute the inner product of the second vector with the third one. So if I denote this by v1, this by v2, and this by v3, then v1 dot v2 will be 5 minus 4 minus 4 times 1, then you have 0 plus 3 times 8, so you get minus 20 minus 4 plus 24, so this is 0. So V1 is indeed orthogonal to V2. So far so good. Then we compute V1 and V3. V1 dot V3, this is equal to 5 times 3 plus minus 4 times 3, then you have 0 and then minus 3, so this is 15 minus 12 minus 3, this is 0. Well, again, V1 is orthogonal to V3. That's good. It remains to check the inner product of these two vectors. In this case you get minus 4 times 3 plus 3 minus 15, minus 3 times 5 minus 8, and here you get minus 12 minus 15 minus 8, and it doesn't cancel with 3, so this is not 0. So V2 is not orthogonal to V3, the set is not orthogonal. The set is not orthogonal. Alright. Now, why distinguish this specific concept? What's the significance of orthogonal sets? It turns out, as the next theorem states, is that orthogonal sets are automatically linearly independent. Theorem. And orthogonal set of non-zero vectors is linearly independent. So if you are given a set of orthogonal vectors, then you know without any checking that it will automatically be linearly independent. And linear independence is a very important property in linear algebra. Now the proof of this theorem is not difficult, so I want to show you how this works. The proof. Suppose your set consists of these vectors and this is orthogonal. Now remember what linear independence is. It means that I cannot find non-zero numbers, some of them non-zero, some of them can be zero, such that C1 D1 plus Cm Dm is 0. So suppose I can find numbers C1 to Cm such that this sum is 0. This means that if some of them are non-zero, it means that the set will be linearly dependent. So what I want to show, right, what this linear independence means that all these numbers have to be 0. If this equality holds, then there is no other way of obtaining it but to choose Ci's to be 0. So how do I prove, for example, that C1 is 0? Well, I take this equality and multiply both sides. I take the dot product with V1. Now, V1, this vector is the 0 vector. So this is equal to the dot product of v1 with 0, and the dot product of any vector with 0 is 0. So here you get 0. Now on the other hand, if you open the parentheses, you will get c1 v1 dot v1 plus c2 v1 dot v2 plus dot 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 cm v1 dot vm. Alright, so and this is 0. Now remember that the set is orthogonal. That means that v1 dot v2, the inner product, and v1 up to v1 vm, they're all 0. So this number is 0, and the next number is 0 up to this one. Alright, so this part of the sum, this whole portion, is 0 because the set is orthogonal. Now, what we got? We got that C1, right, so this is 0, and this is equal to 0. We got that C1, yeah, here there is a typo. You don't get the 0 vector, you get the number 0. We have C1, V1, inner product V1 is equal to 0. But V1 inner product with itself is 0 only if V1 is 0 vector. So this inner product is non-zero. V1 dot V1 is not 0 if V1 is not 0. So this is from previous lecture. That means that if I'm multiplying a non-zero number by some other number and I'm getting 0, this C1 has to be 0. Alright, and then to conclude that C2 is 0, you have to multiply this equality on both sides by V2. And you continue this way, you conclude that all of them are 0. Well, we will not need really the proof itself, but this is an important idea that comes up in several places, and the proof is simple enough, so I wanted to show you. Now, one specific set of orthogonal vectors we already know, and it's a very convenient set. Okay, so the standard basis is orthogonal. If I take V1 to be this, V2 to be this, and V3 to be this, then this set is orthogonal. Is orthogonal set. But there are many more orthogonal sets in R3. For example, we can take V1 to be 3 minus 3, 0. V2 to be 2, 2 minus 1. And V3 to be 1, 1, 4. Okay, and then we quickly can verify that the dot products are 0. So 3 times 2 minus 3 times 2 plus 0, so this is 0, and then b1, b3, you get 3 minus 3 plus 0, so again 0, and then b2 times b3, you get 2 plus 2 minus 4, again 0. So this is again orthogonal, and it's more complicated than the previous set, but it's still what it looks like. If you make a picture of these three vectors, the picture will be similar to this vector. So they form 90-degree angles with each other. So geometrically it's kind of the same, but they are positioned differently in R3. Now, one conclusion or corollary of this theorem that I stated a few minutes ago is the fact that if you have an orthogonal set of m vectors in Rn, then m cannot be larger than m, right? Recall, if v1 Vm is linearly independent in Rn, then m is less or equal than n. So the number of vectors cannot be larger than n. One way to remind you how you prove this, how do we check if a certain set of vectors is linearly dependent or not? Well, you form a matrix, right? So you write this matrix, and then you bring this to echelon form. So linear independence is equivalent to this matrix. So this part is equivalent to every column is pivot column. Right, and the pivots come from the rows. So this matrix is n by m. So there can be at most n pivots, and we have m columns. So to have a pivot in every column, this n has to be larger or equal than m. That's how we get this fact. But if we combine this fact that we discussed in earlier lecture with the property of orthogonal sets being linearly independent, we conclude that if v1 Vm is orthogonal in Rn, then m is at most n. In particular, in Rn, you cannot have a set of 4 orthogonal vectors. So if you're asked to check if certain set of vectors is orthogonal or not, and the number of vectors exceeds the dimension of the space or the size of the vector, then you can immediately say that it cannot be orthogonal, because orthogonal sets of non-zero vectors are linearly independent. All right. Now, orthogonal basis is an orthogonal set that spans the whole space. I suppose W is a subspace N. Then orthogonal basis of W, V1, Vm, is an orthogonal basis of W if this set is orthogonal, if this set of vectors is orthogonal, and it spans W, and the span of V1 to Vm is the whole W. Now, remember what is a basis. Basis is a set of vectors that spans W and is linearly independent. Now, if the set is orthogonal and it consists of non-zero vectors, then by the previous theorem, it is already linearly independent. If this set of vectors is orthogonal and does not contain an orthogonal basis, if this set of vectors is orthogonal and span is this, and none of the vectors is zero. So this is just a technicality. If you throw in the zero vector, it still will be an orthogonal set, but it will not be a basis, because then there will be a linear dependence. Any set that contains the zero vector is linearly dependent. If you go back and look at the statement of the theorem, we explicitly assume that the set of orthogonal vectors consists of non-zero vectors to conclude that they are linearly independent. Alright, so why introduce this concept? Again, it turns out that orthogonal basis is very convenient, because you can compute the expansion of any element of your space in terms of an orthogonal basis by a simple formula. Okay, so how to compute expansion of x in W in terms of orthogonal basis? Well, suppose my basis is V1, Vm. So what we are asking is how to find this C1 to Cm such that x can be expressed this way. If these vectors are not orthogonal, then to answer this question, you have to solve a system of linear equations. So one way to do this, which also works for orthogonal sets, so an old way, works for any basis. What you do, you solve you solve this system. So you write an augmented matrix, you bring it to echelon form, you find the solutions, and a solution, yeah, there will be a unique solution if it is a basis, and that will give you the CIs. Now, if the set is orthogonal, there is much easier formula, which I will explain now. So, new formula. And it is based on the same idea that was used to show that an orthogonal set is linearly independent. What we will do, we will multiply both sides by b1 and see what we get. So we multiply both sides by b1, we get c1, b1, b1, the dot product, and then c2, b1, b2, plus cm, b1, bn. Remember that we are trying to find these numbers. But no matter what these numbers are, we know that they exist. If we formally multiply or compute the dot product of both sides with v1, we will get this expansion. Now, using the orthogonality, this is crucial, all these dot products are 0, except this one. Right, so this is not 0. So this means that C1 is equal to x times v1, v1, v1. This is a nice expression that gives you the first coefficient, and then this works, the same argument works for any other coefficient. So the general expression for CIs, CI is equal x times VI, and then you divide this by the dot product of VI with itself. Right? So basically, if you just take VI and divide by this number, you will get the unit vector that points in the same direction as VI. So essentially what you're doing, you're computing the dot product or the inner product of x with the unit vector pointing in the direction of VI. All right. Here's an example. So we take this old set that we checked was orthogonal. So we take 3 minus 3, 0. V2 was 2, 2 minus 1. And V3 was 1, 1, 4. Okay. And then, so it is an orthogonal set. Set from previous example. Okay, and now let's pick some vector x 5 minus 3, 1. Right? And we want to compute expansion of this vector. Compute expansion of this vector in terms of v1, v2, v3. Now, before I do the calculation, I should point out that because there are three vectors in this set, and the size of each vector is 3, so these are vectors in R3. This is automatically a basis for the whole space. Right? Remember that if you have m linearly independent vectors, then the span is a subspace of dimension m. So if we take W and take the span of v1, v2, v3, because they are linearly independent, dimension of W will be 3. But on the other hand, this W is a subspace, of R3, right, which also has dimension 3, and that means that W has to be the whole space. The subspaces that are smaller than R3 have dimension 2, 1, or 0. This we also discussed in earlier lectures. So this set is really a basis of R3. This is an orthogonal basis. Note that this set is an orthogonal basis of R3. All right. Well, I raised my vectors, but we know what we need to compute. We have to compute the dot product of this x. So C1 is computed as x v1 v1 dot v1, right? And if I do this, I will get 15 plus 9 plus 0 divided by 9 plus 9, this is 4 over 3. C2 is, is not x1, it's just x. X v2 dot v2, and this is equal to 10 minus 6 minus 1, 4 plus 4 plus 4, and this is equal 3 over 9, 1/3. This is not 4, this is 1. And then C3 is x times v3 dot v3 is equal to 5 minus 3 plus 4 divided by 1 plus 1 plus 16. This is 6 over 18 equal 1/3. So x, you can check this directly. It's 4 thread d1 plus 1 thread of d2 plus 1 thread of d3. Alright, so then with the concept of orthogonality, there is the following question that where it has important applications. Sometimes you have a point in Rn and you want to compute the shortest distance to a subspace. This type of problem arises in many problems that come from applications of linear algebra to, say, economics or physics. You want to minimize certain parameters, and suppose the ideal parameters are given by some subspace. On the other hand, you obtain a point that is not quite on the optimal level, but you want to compute how far it is from being in this optimal level. Then it amounts to computing the distance, the shortest distance from that point to the subspace. And computing the shortest distance is given by what is called an orthogonal projection. Essentially, you can imagine that the subspace is a table and your point is a ball, and to compute the shortest distance you just have to drop the ball onto the table, and the distance that the ball travels when it drops on the table is the shortest distance. So that's a version of the orthogonal projection. Now, how does this work mathematically or algebraically? Let's do this with two vectors. So you have some subspace. So this is spanned by a vector v. Okay, and then you have another vector y. All right, and the orthogonal projection is this vector. So you're kind of dropping this ball onto this table. So it is the shortest distance. The angle here is 90 degrees, and this vector is called the orthogonal projection. Okay, and then this other vector that is orthogonal to v and has the property that y is the sum of the orthogonal projection and this complementary vector is called the orthogonal complement. Z of y orthogonal projection of y onto v, and z is the orthogonal complement. Of y to v. right? So this what we have is that this y is the sum of y hat and z, and y hat is orthogonal to z, and y hat lies on the line spanned by b. What we want to do, we want to compute this orthogonal projection. So we want a formula for this y hat. How to compute y hat. Now maybe I will redraw my picture here. This was y, and this was the vector v, and this was the orthogonal projection. Alright? So because this y hat, this vector, lies on the same line as v, we know that y hat is some multiple of v. Now, on the other hand, we know that y is equal to y hat plus z, and y hat is orthogonal to z. So we write this c v hat plus z hat. Okay, so now let's think about this property. What does it mean? It means that the z forms a 90-degree with vector y hat, but this y hat is on the same line as v. So this property is actually equivalent to v being orthogonal to z. Okay. So now we will take this equation and use the same idea that we already applied twice. So we will multiply both sides by v and see what we get. So I will multiply multiply in the sense of dot product. So we take the inner product of v with y, and then that is equal to cv plus z. This is not an inner product, this is a multiple of a vector by a scalar. So now continuing, opening the parentheses, I get c v dot v, and then I have v dot z, and because v and z are orthogonal, this part is 0. So I really get c v v. Okay, this gives me a formula for c. C is equal to this y dot product v, and then you divide by dot product of v with itself. Note that this particular formula came up already in the expansion of a vector in terms of an orthogonal basis. So both of those formulas come out from the same argument, essentially, and you get similar formulas. So if I go back and now substitute this number into the equation, so this is really CV. It's not a dot product, but it's a scalar product of C and V. It's a product of a vector with a scalar. I can now substitute this C so y hat is equal C V, and this is equal to this number V. Okay, so one thing I have to say, this might be obvious, but please do not cancel V. The meaning of V in the denominator and here is completely different. You're taking a dot product. These are not numbers, so you cannot cancel V and V here, and then maybe this V with this V, which you would do with usual numbers. So y hat is not equal to y. Okay, the orthogonal projection is not the vector itself. If you cancel all the v's, you will get the incorrect inequality. And the orthogonal complement, the z, is really y minus y hat. So you can, once you know the orthogonal projection, the orthogonal complement is obtained by subtracting from your vector the orthogonal projection. Okay, so let's do two examples, and that will be the end. Example, compute orthogonal projection of, say, 1 minus 1 onto the line spanned by, say, 2, 3. Okay, 2, 3 is vector, and 1 minus 1 is this vector. And what we want to compute the orthogonal projection here. So in this example, the setup is that this is y and this is v. Okay, so first we compute the coefficient, which is v times y, and then we divide by dot product of v with itself. This gives us minus 1, and then you divide this by 4 plus 9, so you get minus 1/13. So the orthogonal projection, this y hat, is CV, which is minus 1/13 times this vector. You get minus 2/13 minus 3/13. Here's another example. This is the last example. So let y to be 2, 6 and v to be 7, 1. So the question is, write y as a sum of vectors, one of which is a multiple of v, and the other orthogonal to v. Well, this is exactly the sum of y as y hat plus z. So if we consider on a picture, this will be v, and then this is your y, and we want to write y as y hat plus this vector z. Now all we need to do is to compute y hat, and for this we have to compute the coefficient, or the scalar by which we have to multiply v to get this y hat. So here, let me erase the question and keep the vectors. C was y times v, v times v. So you get 14 plus 6 divided by 49 plus 1. So this is 20 or 50, you get 2/5. Alright, and then this y hat will be 2/5 of v, and this is 14 over 5, and then 2/5. So this is y hat, and then to get z, we subtract from y, we subtract y hat. So this is 2, 6 minus 14 over 5, 2 over 5. And if you do this calculation, you will get, let me erase this now, this part. So this z will be 2 minus 14 over 5, and then 6 minus 2 over 5. And this is equal to minus 4 over 5, and then 30 minus 2, this is 28 over 5. So these are your vectors. These are the required vectors, y hat, and the orthogonal complement. So this is the orthogonal projection, and this is the orthogonal complement. Alright, so we'll continue in a week. So I'll stop talking about orthogonal projections and so on. There is a couple of other things to discuss here, but I will finish up on Tuesday in about 10 days. Alright.